To make things even a little easier, I've gone ahead and now divided part 2 up into 2 parts. So subpart 1 and subpart 2. So if you're following along, part 2 is now going to have subpart 1, which will deal just really with screening, and subpart 2, which will deal with graphics. So I think that'll make it a little easier. Again, there's issues uploading these files to the DePaul system. I don't know how other people do it, but I found issues. And also, just to make it a little easier for you, break up the work, I've divided it up into subparts. So part 2 will now have subpart 1 and subpart 2. Subpart 1 deals with the process of actually screening the data. Subpart 2 will deal with visualization, graphics, those types of things. So that's how we're going to divide it up. So we'll start with screening here. Screening, when we talk about screening, we're thinking about 3 things pretty much. Looking for outliers, number 1, looking for non-normal data, number 2, and looking for multicollinearity, number 3. So 3 things we're going to look at under screening: outliers, non-normal data, and multicollinearity. Outliers. Well, what's an outlier, you ask? Well, an outlier is a score that is extremely different from the rest of the distribution. We can have both univariate outliers and multivariate outliers. Univariate outliers are an extreme value on one variable, naturally enough. And multivariate outliers are odd combinations of scores on 2 or more variables. We're going to, for our purposes with this regression class, we're going to deal mostly with the case of one variable or univariate outliers, although not to say that multivariate outliers aren't important, but we're going to deal mostly with univariate outliers. I mean, there's certainly more complex ways of looking at outliers. If you were to take a multivariate analysis, a variance class, or a multivariate class would probably deal with those. But given the nature of this class, I'm going to stick primarily to the case of univariate outliers. So I talked about that data set I created. Again, I created a data set. It's COVID data by state. And so you can see here, one of the first things I did, I used Explore in SPSS to look for outliers in terms of population. And you can see here what you get is basically one of your typical box charts. I call them at least box chart with confidence intervals. And so outliers are going to be those scores that lie outside this confidence interval. And you can see in terms of population, there's no states that have outliers that are below the lower confidence intervals, I guess we could call it limit. But there are cases that have values that are really large. As a matter of fact, there's 4 really large sort of outlier states in the United States, as you can see here. And those would be New York State, Florida, Texas, and especially an outlier, California. I mean, California is a big outlier in terms of population. So you can see the states in the United States, you can see outliers. Oh, one thing I did, I actually deleted from this data set eventually Washington, D.C. I did that. I know there's arguments about Washington, D.C. being a state now, but one of the things you find when you look at the data is Washington, D.C. is a very odd geographic place. I mean, it creates a lot of outlier data and multivariate outlier data, not necessarily in terms of total population, but in terms of things like density and other data points. It was just a really odd, it was really a really odd case. And so, although a lot of people, when they look at states in the United States, include the District of Columbia or Washington, D.C., I ended up saying, man, this is messing up the analyses. I got to get rid of Washington, D.C. because it's sort of a multivariate outlier. I mean, it's got just odd combination of scores all over the place. But we can see there's 4 states that are outliers. I left these 4 states in because what I ended up doing was not using population as a variable, and that removed this problem. But anyway, you can see if I was to use population as a variable, California, Texas, Florida, and New York were outliers. They had extreme values on the population data variable or the population variable. Okay, here's some more outlier analysis. So now we can look at total deaths. So I looked at total deaths and outliers in terms of total deaths. You can see if we're looking at total deaths, there's a lot of states that were outliers. Illinois was even an outlier. So the deaths due to COVID in the state of Illinois exceeded the upper limits of this confidence interval, or the upper point of this confidence band. So then what I did, I saw that there were problems with both total deaths and, if we go back, with population. I said, well, maybe a way to transform this data that would look better, would make more sense, is to use deaths per population, which a lot of people report. So I then went with deaths per population. You can see with deaths per population, the data does look more normal if we're looking just at this explore plot. Now we have two states that have a lot more deaths per population than would be expected. We have two states that are outliers, and those two states are the state of New York and the state of New Jersey, But it does look like using deaths per population makes sense. So originally when I was doing a lot of these analyses, I was using deaths and loading in. We haven't really got to regression yet, but my first variable into my regression was always population, which explained, of course, a lot of deaths. However, as you can see, when we go through these screening and different kinds of analysis, you'll see that total deaths and population aren't very good variables, and it's whatever very good variables means. So I decided to go with the deaths per population variable for most of my analyses. And we'll sort of see more of this as we go along. Okay, now this is, again, to do any kind of analysis with in SPSS. Again, we go to our menu, would go to, again, the analyze, and then would say descriptive statistics, and we can say explore. There are some other options, for example, using advanced unusual case detection programs, but we're not going to be discussing those in here. We're going to stick to using analyze, descriptive statistics, explore. And when we do that, one of the basic things we get is a graphic that looks like this, a basic box chart, and it looks something like this. And again, you can see this would be a distribution of income. You can see there's 1.15 in my data set. That's the income is too high. It's outside the confidence intervals or the confidence range. Now, I don't know what 0.15 is right now. I can, of course, go to that case and look up what it is. Or I could have assigned labels. Like in the previous slides, I had labeled the states by their names. So if I assigned a label here, I could see what case it is that's outside of the income range. Okay, so this is a slide from Field's book. And we're going to see that it has here an outliers example, or it tells us how to spot outliers. So Field is using a data set that he's created. And if you've read the book, you know it's a biologist who's worried about the potential health effects of music festivals. It's sort of Fields has a unique sense of humor, and he is he describes some pretty unique studies in his book, but this is one at a music festival. He's looking at hygiene. You can download the musical festival data if you like. In this, it's data on the hygiene of 810 concert goers over the 3 days of a music festival. And hygiene was measured using a standardized technique. Scores range from 0 to 4, where 0 was you smell like a corpse rotting up a skunk's arse, and 4 was you smell of sweet roses on a fresh spring day. I would probably reverse those if it was my survey, but it's not, it's Field's survey. And then you can see Field shows you how to spot outliers. So if we look at this hygiene data, you can see our graph of the hygiene data. This is a histogram here of the hygiene data. And it's sort of hard to see, but there's a point way out here at 20. And so that's obviously an outlier. When we look at our box chart, and again, with our box chart, we have our mean, median, or mode, our upper and lower quartiles, and then sort of our minimum and maximum expected value in terms of the confidence interval. You can see there's a point, person 611 right up here. That's the one with a score of 20. Now again, if we had cleaned our data, we would have gotten rid of that score of 20. A score of 20 is not possible on this rating scale. So not only is it an outlier, it should have been a data point that was cleaned. But anyway, this illustrates how we can use SPSS to find this outlier. Here again are two more graphs sort of showing similar things. We got rid of that outlier. We're looking at, again, the hygiene data. Now it's all between 0 and 4. You can see we still have one outlier, 0.574. That point is a little outside of our range. Again, one thing though here is, what would you do about 574? It's awfully close. Should you get rid of it? Should you transform your data? I would probably say, my usual decision is I'm not going to do anything about an outlier like that. You're going to have some outliers, some scores that are slightly outside the range. And unless I have 10,000 data points, I'm probably not going to get rid of my outliers. I have to say, I'm a person who I'm very careful and wary about getting rid of outliers. So one thing you have to decide is, even if you have an outlier, what do you do about it? I certainly looked like in the last slide, it was just an error in coding the data. But if it's not an error in coding the data, maybe it's the person's real data. So what do you do about that data if it is in fact their real data? Should you get rid of it? Is that p-harking? So I don't know. I tend to be very careful about not eliminating outliers again, unless I have a clear reason for thinking, well, this outlier should be eliminated. Okay, so moving on, regression, linear regression, makes a number of assumptions. Most parametric tests do. So most parametric tests are based on a normal distribution, and they assume additivity and linearity, normality, homogeneity of variance, and independence. So parametric tests, which are mostly what we're using most of the time, including normal linear regression analysis, assume a normal distribution. They also assume additivity and linearity, normality, homogeneity of variance, and independence. And one of then our purposes of course, screening data is to see if those assumptions are in fact met. So linearity is a tough one because, it's hard to see linearity. And it's hard to see data that doesn't fit linearity unless we just say, hey, I know my data isn't linear. So linearity is not a complex idea. It's the assumption that there is a straight line relationship between the two variables, often would say within the asymptotes. So we might have a lower and an upper asymptote, but within the asymptotes, the data is in fact linear. So that's our assumption. So again, additivity and linearity. We're saying that and especially in regression, so again, this is a regression class. For linear regression, we're saying that the outcome variable, or the variable we're predicting, is in fact, or in reality, linearly related to any predictors. So that between our predictors and our outcome variable, there's a linear relationship. We're also saying that then if we have several predictors, then their combined effect is best described by adding their effects together. That's what additivity means. So additivity is if we have several predictors, their combined effect is best described by adding their effects together. Note, though, that could include an interaction effect. So that doesn't mean we can't add in an interaction effect. And of course, if these assumptions aren't met, those are assumptions of our basic parametric model, assumptions of linear regression, then our model is not going to be valid. So here we can see linearity. The problem is that, of course, a lack of linearity is very, very hard to see. And oftentimes we can get linearity by some kind of transformation of the data. So we might think our data is nonlinear, but it's not really nonlinear. Again, I teach the measurement class. Often the problem is we did a bad job of measurement. So measurement can create what looks like nonlinearity, but the problem is really one of measurement. And so we really have linearity, or we can simply transform the data. So a lot of what are called monotonic relationships can be transformed to create linear relationships. So apparent nonlinearity can simply be an artifact of the data. And what are called non-monotonic relationships are not really that common in psychology. So again, here if we look at this, this would be a monotonic relationship. Monotonic means as one variable increases, the other one increases. Of course, this would be monotonic positive. This would be monotonic and linear and negative. This would be non-monotonic, although it could be just linear, but a zero, to be honest. That's one of the problems. This could be not non-monotonic, just looking at it, but it could be a very low correlation that looks not monotonic. This last one is clearly non-monotonic. You know, a U-shaped curve or an inverted U-shaped curve, that's clearly non-monotonic. That would be very hard to get rid of with a simple transformation of the data. So usually it's fairly safe to assume that there is in fact a linear relationship. Of course, we said we also assume the data is normally distributed. That's relevant to parameters, confidence intervals around the parameter, and null hypothesis significance testing. When does the assumption of normality matter? That's a good question. When does it matter? It matters most in small samples because the central limit theorem says that we can basically forget about normality as we get to larger samples. And larger, in this case, is pretty small. Over 30 is where sort of the central limit theorem kicks in. So we would tend to say when the central limit theorem kicks in, which is sample size about 30, which is pretty small, then we do not have to worry as much about normality. Although it's still true that non-normality is going to affect our analysis. So, you know, saying we can forget about it is sort of partially true, but I don't think totally true. But of course, if we have very small samples, then the assumption of normality becomes a lot more important. So in practical terms, as long as your sample is fairly large, outliers are a much more pressing concern than normality. So again, in terms of screening and normality, again, if normality is not met, actually a lot of times, again, we can do transformations that will give us more normal data. As a matter of fact, we can always force our data into a normal distribution. I mean, there's a way to transform our data to basically force it into a normal distribution. You know, that's as old as teaching itself, right? Hey, I'm going to grade based on the normal curve or the normal distribution. We can always force scores into a normal distribution. So again, spotting normality, you know, it's pretty easy to spot normality. We don't, of course, have access to the whole sampling distribution. By sampling distribution, we mean the sampling distribution of that statistic or parameter. So usually what we do is we test the observed data for normality. But again, the central limit theory says if sample size or n is over 30, the sampling distribution itself is normal anyway. I added this arguably. I would say arguably it's true that if the n is greater than 30, the sampling distribution then, again, that's not saying, when we're saying sampling distribution, we're saying the sampling distribution of, for example, the mean. So we're not saying your data is normally distributed, but we're saying the sampling distribution of the mean is normally distributed. So that if we pull a lot of means from the population of that sample size, they're going to have a normal distribution. That's what sampling distribution means. Again, this is where I would say, I hope you learn this or know this from either undergraduate stats or graduate stats. I'm not going to spend a lot of time on it. Although, again, whenever you say that, that's a dangerous assumption to make. But so I'm going to assume you're sort of familiar with that from before. Again, we can look at normality a number of ways in SPSS, in R, whatever. Graphical displays, what's called a PP plot, is one way to look at normality. Just looking at histograms. We can look at values of skew and kurtosis. Both skew and kurtosis should be near 0 in a normal distribution. There's also a test, the Kolmogorov-Smirnov test. I probably butchered that pronunciation, but that will test if data differs from a normal distribution. Field says don't use this in large samples because small differences will be significant. Don't use it in small samples because big differences won't be significant. I learned about this test in graduate school back in probably 1978 or 79. Since then, I've never once run this test. So I've never once run this test in my whole life. But it is out there. It's a test on whether the data fits a normal distribution. Okay, to assess normality, and again, these are from Andy Field's slides. You can go into SPSS, go into Explore. You can ask for statistics such as descriptives. I would probably check things like SM estimators, outliers, and percentiles here. It asks you how you want to treat missing values. I would agree with his exclude cases pairwise. And although oftentimes what I do is I look at one or two variables at a time. And then it asks you how you want to do your box plots, your descriptives. It's common to get a stem and leaf plot. I never use stem and leaf plots, and I don't really like them. When I look at them, I have no idea what they're telling me. I'm not going to tell you about stem and leaf plots, but if you like them, you can get them. And then, of course, you can also do normality plots with tests. So within SPSS, this Explore, which is under Analyze frequencies, will allow you to do a lot of different kinds of, will allow you to look at a lot of different kinds of data. Okay, we can also, of course, run frequencies, which we can use frequencies to get a histogram with a normal curve. We can also get percentile values, mean, median, mode values, skewness, and kurtosis. That's all valuable, again, in looking to see whether we have a normal distribution. Again, you can see actually Field spends a lot of time on just, do we have a normal distribution? So here's a printout, and we can see both our skewness values and our kurtosis values. You can see that both increase as the days go by. So both skewness and kurtosis increase as the day goes by. It gives you the standard error. I guess, if you're looking at this, you would probably say that, I don't know. Again, I like to look at the plots, whether from just looking at this data, you can tell how big a problem skewness and kurtosis is. I would probably say I can't, so just from looking at the numbers, whether I can tell that skewness and kurtosis are a huge problem. And also beyond that, I'm not sure what you do about skewness and kurtosis if it is sort of bad. Your data is your data. If you have small samples, there's probably relatively little you can do about it. If you have large samples, it probably doesn't matter. So I mean, here it says multiple modes exist. Of course, when you have multiple modes, that can be an issue depending upon how far those modes are apart from each other. You might have bimodal data. But here we look at two different kinds of skew. I always think these are backwards, right? I always think this should be positive skew, this should be negative skew. But don't let me confuse you, it's not. These are labeled correctly. So this is positive skew. The data is sort of piled up like a snowbank to the left-hand side. And this is negative skew. The data is piled up like a snowbank to the right-hand side. So one is positive skew and one is negative skew. Again, if you have positive or negative skew, I mean, one of the things that does impact is your correlation and thus your regression, because it's how well two different variables match in terms of their distribution will put a limit on the correlation coefficient, and thus your regression coefficient. So it's not so bad if one variable has positive skew if the other variable has positive skew as well. As a matter of fact, if one variable has positive skew, you're probably better off having the second variable have positive skew. But if one variable has positive skew and one variable has negative skew, it's going to put a limit on the correlation coefficient, and thus your regression analysis. But it's useful to know what these look like. I mean, again, this could be a positive skew situation. And this is a negative skew situation. So, I mean, this, for example, might be some test that people took that was an easy test. So everybody's getting very high scores. Where maybe this is reaction time. And some people react very quickly, but then there's people who respond slowly, but that starts to drop off. But anyway, that's positive and negative skew. Here we have different kinds of kurtosis. This would be a normal distribution. This is positive kurtosis. It's very tall in the middle. This is negative kurtosis. It's flattened. Again, if you have kurtosis, I'm not sure what you do about it myself. I mean, in terms of solutions, again, you could look into transformations of the data. One thing I wanted to say, and I didn't know where to put it in, but maybe I'll say it right now, is I used to have a professor, his name was Ralph Alexander. He died relatively young, I think in his 50s. He was younger than I was when he died. But Ralph really was a stats genius. And a lot of what Ralph taught me stuck with me. And one of the things he would always say is, hey, if I transform the data, if I transform a variable, what does that new variable really mean? It's really a new variable. He would say it even about taking z-scores. He would say, even if I take a z-score, it's a new variable. So I said before, we can always force scores into normal distribution. We can always do some kind of transformation to force scores into normal distribution. But is it worth it? Because what's that new variable really mean? That was Ralph's point. Every time you do a transformation, the new variable gets harder to interpret. So if we do transformations on variables, what do those new variables really mean? I don't do a lot of, I mean, I'm going to be honest again, I don't do a lot of transformations to get rid of kurtosis. I can't think of one time I've ever done one. I don't do a lot of transformations to get rid of skewness. I can't think of one time I've ever done one. So, I don't know. I mean, I think it's worth knowing if you have real severe problems, but I'm not sure what you then do about it. And you can see also, we call it leptokurtic and platykurtic. So again, platykurtic would be kurtosis that's flattened, and leptokurtic would be kurtosis that's much more pointed. Okay, one of the ways that Field goes through of spotting normality is what's called the PP plot. That's basically a plot of the data. So he talks about getting this PP plot. And so here we can see our normal PP plot. It's a plot of the observed cumulative probabilities versus the expected cumulative probabilities. That's the two P's, I guess. Observed cumulative probability and expected cumulative probability. You can see this is day one. Again, on day one, the data was much closer to normal. And so this plot looks a lot like a straight line. On day two, the data was a lot less normal. So you can see the plot looks a lot less like a straight line. Although to me, I'm not sure, I'd still say it looks that bad. And again, I'd say, well, what am I going to do about it? It's the data. It is the data. But this is the plot of the hygiene data on day two, and you can see it's a lot less normal. Field suggests doing this for groups as well. So in SPSS, it's really simple. You go to what's called split file, and you can organize your output by groups. In this case, he's organizing his output by sex. So we say, OK. We would click on OK and organize our output by sex, and it would give us an analysis. It would give us those PP plots by sex. So this is the split file command again. So now we can look at normality within groups. So if we look at males and females, we can see that skewness, excuse me, skewness, males really get skewed on day 1 and 2 with positive skew. I'm sorry, they really get, for skewness, they get positively skewed on day 2, somewhat positively skewed on day 3. For kurtosis, really bad on day 2, although then it's negative again on day 3. For females, the results are pretty much the same, although not as severe. Skewness, they start out negative, positive on day 2, getting near 1, positive on day 3, getting near 1. For kurtosis, starts out negative, as did males, but doesn't go way up. I mean, if we combine the males and the females, it's very different in terms of kurtosis on both days 2 and 3. So I guess if you looked at this, you could say the female data stays more normal, stays closer to normal distribution than does the male data. And here we can see this is day 1 for males and females. Again, we said day 1 was pretty normal. And we can see this from these plots of observed versus expected values. Okay, we're going to move on here to homoscedasticity and homogeneity of variance. Again, this is a basic assumption of regression of a lot of parametric tests, homoscedasticity or homogeneity of variance. They're related concepts. Homogeneity of variance is that when testing several groups of participants, samples should come from populations with the same variance. So homogeneity of variance is just saying different groups should have the same variance. And in correlational designs, then, the variance of the outcome variable should be stable at all levels of the predictor variable. So that's really the homoscedasticity assumption, that at different levels of the predictor variable, the outcome variable variance is stable. So here we can see homogeneous variance and heterogeneous variance. Again, this is for different groups. So these are different areas of England, different geographic areas of England. We're looking at ringing in ears and hours for different groups in England. And we can see in the first case, the data is pretty homogeneous in terms of our variance. So these are our means, and these are our confidence intervals around the means. You can see the confidence intervals stay pretty similar for this comparison. So this would be homogeneous data. So again, these are the means. this shows you the variance. And you can see that these confidence intervals are pretty similar. So this would be homogeneous data. Here you can see they're jumping around. Different geographic areas have very different variances. Again, these are means, these are variances. So in this case, we would say that the data is heterogeneous in terms of variances. So it's a pretty simple concept. If we have two groups, say male and female, homogeneous means the variance is equal for the two groups. Heterogeneous means the variance is not equal for the two groups. Homoskedasticity and homogeneity variance can affect the two main things that we might do when we fit models to data. And that is looking at the parameters and looking at null hypothesis significance testing. In terms of assessing homoskedasticity and homogeneity of variance, we can do graphs. We'll look at that when we get to our lecture on regression. There's a test called Lavern's test. Lavern's test tests if variances in different groups are the same. You shouldn't use it if you have large samples, because then small differences will be significant. If you have small samples, because big differences will be significant. Although actually I would say with small samples, if you only have a couple people, you can get really odd variances. So with small samples, small differences, big differences can be significant, but they can be very artificial because you're calculating the variance on so few people. Of course, if you violate this assumption, there are some solutions. There's some tests that are robust to violations of homogeneity of variance, although I think there might be some people who argue that's not so true. And we can always do adjusted standard errors. You can do bootstrapping too, although he doesn't include it among his solutions. But so there are some solutions. And I mean, again, this is a difficult topic because I think the question is, for me, the question is always one of, are you really hypothesizing that there should be homogeneity variance? You're getting homogeneity variance, but is there a good reason for that homogeneity variance? Is it true homogeneity variance, or is it because your samples are in some way oddly restricted? If your samples are oddly restricted, it introduces new problems or new issues. But the reality is, in a lot of studies we do, I mean, again, I think one of the problems is in a lot of research, especially when using archival data, the data may have artificial restrictions and restrictions of range that contribute to what looks like homogeneity of variance or homoskedasticity, when really in the population it doesn't occur. But then the problem is, what do you do or how do you correct for that? I think the problem is the corrections get very complicated. Okay, the last kind of screening is for multicollinearity. Multicollinearity is a big word that means variables that are highly correlated with each other. Of course, the question is always, what is high? Probably some people would argue if most of our variables don't have reliabilities of more than 0.80, then a 0.80 correlation between variables is almost really a perfect correlation. That's probably multicollinearity, they would argue, but you find people who disagree with that. So anyway, multicollinearity variables that are highly correlated. You can have both bivariate multicollinearity, where two variables are highly correlated with each other, or multivariate multicollinearity, where when you combine variables, they're then highly correlated with another variable. Both of these problems are related to what's called singularity, which is the redundancy between variables. For example, which you shouldn't do. I mean, again, this is something you should clean, right? That shouldn't occur in the first place. But for example, if you're using both subscales and a total score in one analysis, the total score is going to be totally dependent upon the subscales, which is going to lead to singularity. So that's a redundancy between variables. It's going to create multicollinearity. But the fact is, you should not be doing that in the first place. If you're doing it, it's a mistake. Anyway, again, if you haven't noticed, when the slides don't say field, they're not field slides, they're my slides. So there's both field slides and my slides. My slides won't have the field information on it in general, unless I made a mistake and kept in his format, or in a couple cases, I just added to his slides. But so this is one of my slides. My question, when is high too high? I see we have a typo there. And then one of the things I'd also say, I notice when people collect data with mTurk, correlations get a lot higher than what they used to be with data. I think that's an artifact of mTurk. I'm not a big fan of mTurk, but I know it's the way the world's gone. But a lot of times when you use mTurk, you're going to see that your correlations are too high. Okay, our next topic and last for this section is power analysis. I can tell you right now, I don't believe in power. I mean, I believe in power. I just don't believe in worrying about it. Because I can tell you right now, unless you're doing big data analysis with 10,000 or a million cases or whatever you have, you probably don't have enough power. So that's why I say I don't do it. I don't really do power analysis. I don't believe in it. I think, you can pretty much say right up front, you don't have enough power. So I don't see the value in the typical psychology situation. I think people are just fooling themselves with a lot of their power calculations. But I do think there's some general guidelines we can give. I think you could start by saying if you don't have at least 30 people per cell, you're in trouble. So if you're doing sort of a traditional analysis of variance and you don't have 30 people per cell, you're in trouble. If we convert that into regression, that really means that if you don't have at least 30 people per variable for regression, not 10 like some people suggest, you're probably in trouble. That's true unless you're an engineer. Now, engineers get R-squareds of above 0.90, but in psychology, we don't get R-squareds of 0.90 very often. So I would say unless you have, n sizes in a regression analysis of 30 per variable, you have a problem. Not a lot of people run regression analyses without 30 per variable. But again, unless you have 30 per variable, I'm not even sure why you're worried about power. You definitely don't have enough power, probably. And so, that doesn't say you shouldn't run the analysis. It just means you probably really don't have enough power. So I'm saying these are not the numbers to get really strong power. These are probably minimums. I would say some minimums are 30 per cell for ANOVA if you're not adding anything like covariates or control variables. For correlations, you should have at least 100 people per cell. And for regression, again, I'd say you often see at least 10 people per variable. I'd probably say 30 people per variable, but that's me. And so really to get power, adequate power, we probably need much larger sizes than we're typically using, unless, again, you're doing some kind of big data analysis. Again, that's why I think a lot of people, including myself, would recommend meta-analysis. That doesn't mean you shouldn't do a study, but it means really what we should be depending upon is conclusions, interpretations, results that come from meta-analytic investigations. If you do want to do power analysis, there are various programs. G-Power is a well-established free program for most basic analyses. For structural equation modeling, there's often it's their own programs, or even a lot of SEM programs have their own ways to do power analysis. There's also rules of thumb, but again, I myself just am not a big fan of power analysis. I think most of the time people are just fooling themselves, and for a lot of the typical theses or dissertation, I can probably tell you you don't have enough power without even doing a power analysis. Okay, and then what if all else fails? What if, we talked about these assumptions, normality, linearity, additivity, avoiding multicollinearity, homogeneity of variance. We talked about these things. But what if you have them? Well, again, some people would argue, hey, the not parametric statistics are actually pretty robust to violations and assumptions. I think Field argues, well, there's alternative statistics you can use, or you can use Bootstrap, and Bootstrap gets around some of the problems if we violate assumptions. You can, of course, move to use of non-parametric statistics. You can just try to do simulations, not collect real data because real data is messy. Or, of course, you can give up and find another topic to work on. That's probably the last alternative. This really isn't the end. This is the end, though, of what we're considering to be part 2, subpart 1. So part 2, subpart 1, we'll be moving on and we'll be doing part 2, subpart 2, which will get into graphics and visualizing things and some other areas. But that will now be subpart 2 because I divided these up. So part 2 has a subpart 1 and subpart 2. This is the end of subpart 1 of part 2, but we'll be moving on to part 2, subpart 2. So see you there.